this is our number 1.34980,655, which we have obtained after dividing by a power of 2, and we need to convert that into binary form. So what to do? To write this thing down in a calculator, and we need to have the fractional part. So we are going to subtract 1 from it, and if we are going to subtract 1 from it, we are going to get a fractional part. Now for that fractional part, we are going to multiply that by 2. So if I'm going to multiply 0.02, so I'm just going to write the first 4 number, but in your calculator you should have all those 4 digits. So if I'm going to subtract 1 from it, this number becomes 0.234. Now I'm going to multiply this by 2, right? And I'm going to see if my answer is greater than 1 or not. So if it's greater than 1, I'll write 1. If it's less than 1, I'll write 0. And then I'm going to continue with this. So if I'm going to multiply this by 2, what I get is 0.46. So this number is going to be less than 1. So I get 4.469, and there are more digits, but I'm not writing that down. So this means my first digit here is a 0, right? So my first digit here is a 0, right? Then I'm going to use the same fractional part multiplied again by 2. Obviously, since this is less than 0.5, I know that it's going to get an answer which is always going to be less than 1 as well. So I'm going to still multiply by 2, and what I'm going to get is 0.9399, and then there's a big number, so I'm just not writing the whole thing down. So again, less than 0, less than 1, so it's going to be the second bit is going to be 0 as well. Now I'm going to multiply by 2. So obviously you have got 0.9. If you multiply by 2, you're going to get 1.8 something. So again, multiply this thing by 2, and you are going to get 1.87. So now you have a number which is greater than 1, right? Now if it's greater than 1, then this means you are going to write a 1 over here, right? So this is what you are going to do now. But then there is one thing special over here. So if you get a number which is greater than 1, how are you going to continue further? So in order to continue further, we do the same thing. We subtract that 1 and get the fractional part out of it. So we just don't multiply the same thing by 2. We take the fractional part and remove that 1, because we have inserted that 1 over here. So subtract the 1 from this number, right? And what you're going to get is 0.879, and then you're going to multiply this by 2 to continue on. Obviously this number is again greater than 0.5, so you're going to get a number greater than 1 again. So whatever you are going to get, then you are going to do the same thing on it, like you are going to get 1.75. So again the same thing, this number is greater than 1. So we are going to write a 1 over here, and if I'm going to continue, then I'm going to continue from 0.759 something, right? So this is how you're going to continue. Okay, so this is how you're going to continue, and you're going to do that as many times as required. For example, if you're talking about a single precision number, so single precision has got 23 bits for the floating point to store the fractional part. So you're going to do that 23 times. It's a tedious work, but so we have done that already 5 times. I'm just illustrating it for you, and that's why it's a little delayed. But once you're going to do that on calculator, it gets a little faster. This is the only way you can do that on a manual computer. So it's on a calculator. So this is how you're going to do that, and you're going to calculate the bits. Okay, so I'm going to just come to that answer. The answer for this is 0011. So you see, we did the first 4 bits up till now, and there was a hidden one as well, so that this one is not going to be stored. So we are going to just store the fractional part, and you're going to do that 23 times, and whatever number that you have, you are going to put it over here. The other thing is we had 82, and 82 obviously will be stored after introducing the bias to it. So 82 was the number, add 127 to it, and then you're going to get whatever answer you're going to get. You're going to convert that into binary, and this is the binary equivalent of that. And since this was a positive number, you have a 0 over here, and this is what you have stored. So this is what you have stored in a single precision format. So in order to find out what actually this number is this actually 5.972 into 10 to the power 24? So we need to do a reverse operation, right? So we can do a reverse operation as well. Again, it gets a little it gets a little tedious to do that because you have to add the powers of 2, but you can do it. It's nothing very difficult. You just have to take a calculator and start adding the powers of 2. So first identify which powers are going to do that to be added. So I won't do it because we are a little out of schedule and we don't have much time for the main lecture today. But the main thing here is this number here. This is 2 raised to the power minus 1, minus 2, minus 3. So you have got a minus 3, a minus 4, minus 5, and minus 6, right? So you have got 2 raised to the power minus 3, minus 4, minus 5, minus 6, and 11, 14, 15, 16, 17, 19, and 20. So these are the powers of 2. So what you can do is you can just write that down. So you just write that down on a piece of paper. So 2 raised to the power minus 3 plus 2 raised to the power minus 4. Or if you don't want to write it down in a piece of paper, you can directly add these powers on a calculator. So 2, 3, 4, 3, 4, 5 were there. What else was there? So we had 3, 4, 5, 6, and 11, and so on. So you can just continue on adding those powers of 2, and then what you're going to get is a number which is the fractional part, which is going to be a fractional part. So if I do this thing and continue on with all these powers, so the last one was 2 raised to the power 20, I think so, right? Sure. Right. So you add all of those powers. Yeah, 20. It was 20. So you add on all of those powers, and then you're going to get some number, right? And this number was the fractional part, so you are going to add one more to that, so it would be 1 point something, right? So the whole thing here is going to be come over here, and it will be something over here, and this is the fractional part, and then you're going to multiply it by 2 raised to the power the same exponent that you have. So this exponent here is what is this thing? It is 128 plus 64, that would be 196, and 196 plus there is no 32, there is 16, and then there is a 1, so 17. So so what we have is a 96 plus 17, 96 plus 17. So that would be 113. No, sorry, and sorry. It's not. It's 128 plus 64 plus 17. So that's 209. So this number here is 209, right? But you have to subtract the bias before calculating the exponent. So subtract 127 from this number, and what you're going to get is the same thing, 82, right? So this is the same thing, 82, that you're going to get. So if you're going to put that thing back into the exponent, so from the power of 2, you are going to calculate the fractional part, and then you're going to put that the exponent part back, and this is how you're going to get whatever number you have stored. So I did that for you. You can do that yourself as well. So I'm going to just show you the answer. What is the number that is coming over here? So if we do the reverse operation, what we are going to get is not exactly 1.234980655. Rather, what we are getting is this number here, 1.234980583. So see here, there is a difference coming at this point, 80655. This is 80583, right? This is according to how we have done that reverse operation, adding the powers of 2. Because this is because we have done that for 23 steps. Had this been a double precision number, we have got 52 bits for that, and we could have continued the same process and it would be much more accurate than this one, right? So this is why that is called as a double precision number, because of its accuracy. You add more powers of 2 to refine that. Remember that this number that you are going to get is always going to be less than that, right? So this is an important thing. So because these are the powers of 2 and you have stopped that operation at 23 bits, if you had continued that operation, this number would have been much refined and it's going to add more numbers to that. So more powers of 2, if you are going to add that, that number is going to increase. So 583. So actually was 655. So if you could do that for 52 bits, you're going to get closer to this 655. Still, it won't be 655. So if you just reverse this process on a calculator, what you're going to get is 5.97199.655 in 10 to the power 24. So actually we wanted to store 5.972 to 10 to the power 24. What we stored is 5.971999655 in 10 to the power 24, which is, you can say, quite different from this number. Okay. What seems like that this is a very big. So if you just subtract these two, you're going to see that the answer that you're getting is a very big number, right? So I'll do that subtraction. So if I do, for example, a 5.972 exponent 24 minus 5.971 999,655 exponent 24. So my answer that I'm getting is 3.45 in 10 to the power 17. Wow. So that's a very big number, right? So the answer, the difference I'm getting is 3.45. You can do that yourself as well, into 10 raised to power 17. So that's a huge number. Oh, sorry, not minus 17, 17. That's a big difference. Okay, so we wanted to store something and we had stored another thing which has a difference of this thing, 3.45 times per 17. Right, so now I'm going to come to the main point. So main point is that we don't do the subtraction like this. We don't find the error or the difference in value by just subtracting. We find the error by taking the percentage difference, not the main difference. So we take the percentage difference. So actually what this the difference is from your actual value and the value you have stored. That is this difference. But you're not going to store, you're not going to be interested in this value here. You're going to be interested in the percentage difference. And if you want to calculate the percentage difference, then you have to divide this by the main amount that was 5.9. What was that? 5.972 times to the power 24. So if you do this, then you are going to get something which is significant. So 5.972 into 10 to the power 20. So if you divide this with its primary number, then you are going to get some value. So if I do that, this is going to give me the percentage error, and that error should be small. So if I do that, so this is going to tell me that this difference here is of what order. So that number I'm getting is 5.77 into 10 raised to the power minus 8. Now this is a small error. Actually there is an error, but yeah, minus 8, right? 10 to the power minus 8. And if you convert this thing 10 to the power minus 8 into its binary form, you're going to see that this order is around 2 raised to the power minus 24, right? Of the order of 2 raised to the power minus 24, which is our main task here, that we have to you reduce the error up to unit of least precision divided by 2. So unit of least precision, as you all know, in single precision is 2 raised to the power minus 23. So this thing, if you convert it back into its binary form, it has an error 2 raised to the power minus 24, which means that this is the maximum that you could have stored in 23 bits. Okay. But had this been 52 bits for a double precision number, then this error is not acceptable because you are getting wrong bits for the 24th bit, and this means for single precision this error is fine. So this error, whatever number you're going to store, and if you want to take that number back, most of the time you're going to see that there is going to be some error, and this error is never going to exceed 2 raised to power minus 24. So this thing should be uh, uh, you should keep this in mind, that the error should not exceed the unit of least precision divided by 2. Okay, right. So this was about floating point number. If there are any questions in conversion, then I can just quickly answer that so that we come to our main topics. Yes, any questions here? It gets a little confusing for the first time, but if you're going to do some practice, then it's going to be much easier. Obviously we are not going to do that uh, in our course. This was just for an explanation, because we are dealing with floating point numbers. The first question that comes to mind is, how can I convert a number into its equivalent floating point value? So normally we can have a program for that, and then but if you want to do that manually, this is the procedure that I've told you. And this is a complicated thing, but normally we don't do that by hand. So if you want to convert that, there are computer programs for that. So if you want to find, if you are building an application that converts a number into its floating point value, there you are going to find different APIs for that as well, which are going to do that for you. But if you want to write your own program, this is what I have told you how to do that. Okay. So right. So any questions here? I'm waiting for some question or some response. Is this clear? If it's clear, then I can just, okay, so I can move forward. So there were some other exercises as well, like another number like 0.794265 into 10 power into 16 raised to power minus 16, and this was a number written in base 16. So this is not base 10 over here, this is base 16. So if it is base 16, this is simple, because you can express every digit in 4 bits. And if this is power of 16, that is also simple, because it's actually 2 raised to power 4, and 2 raised to power 4 multiplied by minus 6, 2 raised to power minus 24. Then this becomes quite easy to do. So you can do that. I've written the answer as well. And that was last week's date. So it was 6th August 2020. And this is your home exercise. You should do that yourself. And you can also calculate the errors in each case. So as I've mentioned, the errors are basically not the differences in the value stored, but the differences divided by the actual value, and that error has to be kept, is always going to be less than 10 raised to power minus 24. Okay, so now I'm going to come to the floating point arithmetic. So we have discussed about floating point numbers, how to store them, how to convert them. Now let's come to the arithmetic part. Now, when you're talking about arithmetic, the basic operations are addition, subtraction, division, and multiplication. So we can do all of these operations, but they are always going to be imprecise than its actual form, right? And this is the problem with real numbers, with floating point numbers, not with real numbers, with floating point numbers that are stored in computer. That because of the limited storage capacity, there is always going to be some error, like we have mentioned over there. And then if you're going to do some operations on them, that error is going to accumulate. So it's going to add up the error value. Sometimes the error is going to decrease, but sometimes it can accumulate as well, right? So for some operations, if you keep on adding the values of different numbers, they have their own errors, but when you keep on adding them, then the error also accumulate. But if you are adding and subtracting, then sometime it happens that the error reduces. Okay, so our task here is to get the value which is as close to the unit of least precision by 2. Now I'm going to have an example over here. So if we have these two numbers, which is 1 plus 2 raised to power minus 1 multiplied by 1 plus 2 raised to power minus 23. So what should be the answer here? What should be the exact answer here? Is anyone? So this is a number which has a 1.1 because 2 is to minus 1, so there is a 1 right after the decimal point, and 2 is to minus 23 means there is a 1.000000 and the last bit is a 1. So we need to multiply these two floating point numbers, and what should be the answer? That's easy. Come on.
1.5,
No,
1.500.
no, I'm not talking about the exact answer. If you can just mathematically tell me what should be the answer, because this is a very simple question of a plus b multiplied by uh, b plus c or a plus c,
So we
whatever.
can just add the powers. The
Yeah,
bases are
how do you do that mathematically? So if you have got two numbers, a plus b multiplied by c plus d, so what you do is a into b and a into c plus b into c plus b into d, right? That is how you do, right? So the exact result would be 1 into 1 and 1 multiplied by 2 is to minus 23 and 2 is to minus 1 multiplied by 1 and then 2 is to minus 1 multiplied by 2 is to minus 23. So the exact result would be this value 1 plus 2 is to minus 1 plus 2 is to minus 23 plus 2 is to minus 24, right? Okay, but what we cannot store this 2 is to minus 24 because we have just 23 bits. Okay, so the result that we are going to store is going to be something like this: 1 plus 2 is to minus 1 plus 2 is power minus 23. And if you want to truncate it, then you are going to store 1 plus 2 is power minus 21 plus 2 is power 23, right? But in both these cases, either it's 1 plus 2 is power minus 1 plus 2 is power minus 22, or it's 1 plus 2 is power minus 1 plus 2 is power minus 23. The error is less than half, is actually equal to half of unit of least precision, which is 2 is power minus 24, right? So this is the rounded result because we have taken this and rounded it off, and when we are going to round this off, this is going to become 2 raised to the minus 22, right? Right or not? Yes. Are you getting this? Okay, so we had 1 plus 2 raised to the minus 1 plus 2 raised to the minus 23 plus 2 raised to the minus 24, and we say that we have to store the value in 23 bits only. Okay, so if you're going to truncate it, truncate means okay, I'm going to write first of all its binary equivalent. So this is actually 1.1 and there are many zeros, and the last two numbers are 1 and 1, right? So we have to we can store only 23 bits. So 23 bit comes till this point, right? So how are you going to do that? So one value is to truncate it. If you're going to truncate it, you're going to leave that extra one, and this number is going to be 1 plus 2 raised to the power minus 1 uh, plus 2 raised to the power minus 23, because you have truncated it. The other option could be to round it. When you're going to round it, what you do is this extra 1 2 raised to minus 24 is going to be used to add one more to this number, and if you're going to add one more to this 2 raised to minus 23, it's going to become 2 raised to minus 22. So this number would then become 1 plus 2 raised to power minus 1 plus 2 raised to power minus 22, right? So that was 23, it becomes now 22 because we have, for the rounding, we are going to put one more number over here, add one more to this. And if you're going to add one more to this, then this becomes 1 0, which means 2 raised to minus 22. So in both these cases, the error of storing the actual number. So if you're going to subtract this from this, what is the value that you're going to get? What is the difference in these two? 2 raised to minus 22, 24, right? 2 raised to minus 24 is the unit of least precision divided by 2. And if you are going to subtract this and this, again the same thing, 2 raised to minus 24, right? Because
so why 2 raised to the minus 24 when we are rounding it off?
when we are rounding it out, so when you're rounding it out, so if, for example, if you have got a number like this, 2.476 and I say that I want to have just two digits after decimal, how are you going to do that? You are going to write 2.48, right?
Yes, sir.
This is what you do in rounding. So the same thing is happening over here. So why do you have to 48? Because you know that this thing here
This is
is
5.
greater than 5, right? So this is because you need to have it in the least possible error value. So you then convert it. If it's less than 5, you are going to leave that as 7. But if it's greater than 5, then you are going to add one more to it, and it becomes 8, right? So this is the same thing happening over here. That if there is a 1 over here, this means there is some value. If had this been, this bit being 0, then there would be a different technique to round it. Uh, if this was a 0 and there were many zeros over here, then you wouldn't have done a similar thing. Or if there was 0 and then there was some ones over here, then perhaps you won't have added a 1 over here to it. But if you're going to add one more, then this is. So my question is, if we take the error for this and this, what would be the value? So if I subtract this and this, the difference, so what is the value?
2 raised to the power minus 24 and 22. Both of them will be left.
So what would be the value? 2 is if I subtract this, so this and this cancels out. Okay, so we are getting 2 is power minus 23 plus 2 is power minus 24 and 2 is
Yes.
power minus 22. So what's the error? Come on, this is simple. Okay, so the main thing is, this is your value 1.0 1.100, and there are many zeros, and then there is a 011, right? uh, what I am storing is 1.100 and 100. Okay, this this
Yes.
this, this becomes easier because this is minus 22, this is 23 and 24. So what is the difference between these two? Come on, the difference is 2 raised to minus 24. Because if I add this 2 raised to minus 24 to this number, it will become this number, right? If I add a 1 over here, it will become this number, right?
Yes, sir.
Oh, so this means that this is the difference, right?
Yes, sir.
Okay. So there is only one student saying yes. What about the others? Okay, so this was the thing that we have discussed over here, that if you're talking about arithmetic between two floating point numbers, the main thing that you are concerned with is that the error of the final result should not exceed half of the unit of least precision. Okay, so let's come to our basic operations: subtraction and addition and subtraction. How do we add two floating point numbers? Come on. So first of all, I'm going to ask you people, if you are given two floating point numbers, how do you add these numbers? So I have a number like 7 points. I'm going to go with decimal. 7.48 into 10 to the power 16, and I need to add this with 2.58 into 10 raised to power 18. Okay. Yes, anyone? How am I going to do that?
We can make the powers same and then we can add
Okay,
the two.
right. The first thing that we have to do is to have these powers similar, because we cannot add numbers which have different powers, right? So was there anything in the chat? Make power same, Fat Khan. Fat Khan, you're not saying anything, just writing it down. Acha, microphone not working. Okay, that's fine. Okay, so yeah, this happened in online classes. This is something that, because we have not prepared for it, that's possible. So I don't really blame students for that, because this is a special semester. uh, we are just continuing with how with a different technique to study. Okay, so the main thing is that we have to make our bases same. Sorry, bases should be same. That is the case there, but the exponential values should be same. So we have a 16 and an 18. Now, if you say we have to make the base same, so let's try to do it in two different ways. So what I can do is I can say this number. So I'm going to do it in two different ways. So write it over here. So what are the two different ways? So I can write this as 0.0748 into 10 raised to power 18 and added with 2.58 into 10 raised to power 18. Okay, so this is one way to make the power same, and the other way could be to have 7.48 into 10 raised to power 16 and add it with another 2.58 to 58 into 10 to the power 16, right? Fine. Point zero. If I can write point zero also to make it clear. Yeah. Okay.
Clear, sir.
Okay. Good.
So,
Which of these two are you going to select? Or you say that both are correct?
so both of them are correct.
Both of them are correct.
If
Uh,
someone wants it in standard form with one place to the left of the decimal point, then he can select the one with the power 18.
hmm.
That is the
Um,
standard.
yeah, but it might happen that eventually what is for example it had it this been instead of 2 it was 9 over here, and we had a number which is going to give some carry to this bit, so 9 becomes 10. So eventually you are going to have a final answer which are going to have two bits, two digits before the decimal point. So this can't be a rule that there is always going to be a single digit after a decimal point in our final answer. So they can be two digits as well. So, but yeah, which one seems better? Either do it this way or this way. So there is a technical answer for that.
Sir, both are okay. It's personal preference whether
Sir,
you think of left side or right side.
Yeah, but it could be a personal preference if you're talking about doing it on paper and pencil, because both of them make sense, right?
sir,
And
nothing.
finally you are going to whatever final answer you are going to get, you are going to ensure that there is a single digit before the decimal point, and if there is any normalization needed in the final answer, you're going to do that normalization shift as well. But the question is what should be done, because what the two numbers that I have selected have a small difference, 16 and 18, right? So had this been 6 and this been 18, the difference between these two would be larger. The difference
Yes.
between the two exponents is just 2, so you have either to shift to the first number or the second number. But if the difference is larger, for example this was 6 and this was 18, then the difference was something like 12. So if you're going to do that 12 times, then there is a big problem over here to do it this way or to do it this way, right? Both of them will have 12 shifts involved to align them, but there is a difference between these two shifts. Now I'm going to come to that. So we are going to select this one here. Why? Uh, okay, so there is a technical difference here. Now when we have two numbers like 7.5 into 10 to the power 16. So I forgot what that number was, but I'm coming up with another example. 7.5 to the power 16 and something like 2.8 into 2 to the power 18, 10 to the power 18. So we go with shifting the smaller number. Now when you're going to shift the smaller number, we are calling this smaller because of this. It has got a lower power. So we are always going to shift the smaller number. And this number, because it has got a lower exponent value, it would be shifted to make this significant part even smaller, right? So that this thing becomes bigger. So the exponent value goes bigger. So the magnitude has to go to reduce. But the magnitude is going to reduce, which in other way means that you are going to shift right, right? So you are going to shift right means that you are going to divide this number by some powers of 10 in this case. So this thing converts to, uh, if you are going to do that twice, so that becomes 0.75. So what you see, what you have done is you have reduced the magnitude of the smaller number. Now, why is this important? This is important because in computer arithmetic we have limited space. If the difference between these two exponents was just 2, so we have shifted it for two numbers. But had the difference between a very big value like 10 or 15 or something even bigger like 20 or 50, then you're going to see that shifting a smaller number to the left means you are reducing their magnitude. And if you come to a point where you have to keep your number in certain limit, then you are going to lose certain bits or digits. If for a smaller number to shift right means that the digits which are going to be removed are very insignificant digits. And then if you're going to remove that because of space consideration, because you just have 24 bits to hold that thing or 32 bits to hold that thing, then this means that the bits that are shifted out already had a very less significant value, and then they could be removed because the final answer does not depend on them. But for a bigger number to shift left, because this is what happens when you're going to shift the number, the bigger value, you are going to shift it to the left. And when you're going to shift left, the magnitude becomes higher. So when the magnitude becomes higher, the exponent value becomes lower to be equivalent for that. So when the magnitude becomes higher, you have to keep on all these values with you, because they are all with the significant values. So this is the most significant number of these two, because this is a bigger number. And if for example the difference between these two is something like 20 bits, so if you're going to shift this 20 times, you have to keep all those 20 bits. And if the difference between these two numbers is something like 100 bits, then you have to keep all those 100 bits, because you cannot try to remove any of these bits or try to think of excluding any of these bits. So for example, if I shift left and remove this 2 because I have constraints of holding the whole thing, then the final answer is going to be a totally different answer, because this 2 is the most significant digit in this case, right? And if I remove this, then the whole answer gets changed. So if you're talking about adding two numbers, the first thing is we have to make the exponent value same. But for making the exponent value same, there are two ways to do that, and then the best way to do that is to remove to make the smaller numbers go to its left, to its right, so that you are going to reduce the magnitude. And if in that process you remove some bits, those bits are going to be of the least significant values, right? So I'm going to come back. Is this okay? So so when we are going to add two numbers, we are going to ensure that they both have the same exponent values. And if one of them has a different value, then you are going to shift the one which has the smaller exponent value to the right, right? Now that type of shift is sometimes called as a pre-shift. So if you have got two numbers here as shown, so this is our first number S1 b raised by E1, and the second number S2 b raised by E2. So if you want to add them, so what you are going to do is say if E1 is greater than E2, then we have to do our operation on this number, which is the smaller number. So what you are going to do is you are going to make this equal. So you are going to make E1 over here, and for doing that you are going to reduce the magnitude by that amount, which is the difference of these two. Okay, so what you're doing is dividing it or shifting it left, shifting it right the same amount. And in this way, what you are left with is this significant value with the same exponent. And finally, sometimes you might need to have a normalization shift at the end, right? So this is an example over here which expresses the same thing. What is going to happen if we add two numbers, 2 raised by 5 and 2 raised by 1. So we are always going to go with the smaller number first. We are going to shift that smaller number to the right, and if you're going to do that, this becomes something like this: 0.000. So you have shifted it 4 times because the difference between 5 and 1 is 4. So we shifted it 4 times, and so this decimal point comes from here to here, and then the exponent values are same. Now what you these are the extra bits. So if you don't have space to store them, you can remove them in the addition process, because these are the least significant values, and if they are removed, they are not going to be part of the final answer. If you have space, then you are going to consider them in your final answer as well. And the final result is going to be the addition of these two, which is going to handle that. If you don't have space, then you are going to remove that. Normally, what happens is when you are doing addition, we don't do addition in exactly the same number of bits. So for example, we have got 23 bits for significant value. We are going to bring back that hidden one, that becomes 24 bits. So when you do calculation, you're not going to exactly have an adder of 24 bits adding with 24 bits. For these types of shifts, we have a bigger adder when you are going to add these numbers. So that happens in the calculator as well. What the calculator shows in terms of digits is a different thing in the answer, but internally it has got capacity to hold more digits. So this is why if you keep the value in the capacitor in the calculator's memory and do another calculation, then it's going to give you a different answer than if you write that whole thing of 10 digits down into the calculator bits and do the same thing. So that will be a different answer, because the calculator also holds the value in its memory capacity, which is greater than the number of bits over here. So for example, in this example, we had a 1 2 3 4 5 6 8 bits after the decimal points. So because of these shifts and the adder which are going to add these two numbers, normally it happens that we have a bigger adder which is more than 8 bits long, and then we can add these 2 bits, and finally we're going to remove these bits after rounding it off. So how many extra bits do we need? That's another topic which we are going to come at later. But you don't really have to store all these bits, but there is a way to determine how many extra bits do you actually need in your final to get the same accuracy as much as accuracy as required. Okay, are we clear till this point? Are we clear to this point? Any questions here?
No.
Any questions here? No. Okay, fine.
No, sir. Thank you.
Okay, so now this is the main thing here. So I'm going to come to the multiplication process after the break. I'm going to take a break shortly, but let's just finish the floating point addition process. So when operand signs are alike, a single bit normalization shift is always enough, as the result is going to come within the space of 4 to 1, right? So when we have got floating point numbers, and we say there is always going to be a single 1 before the decimal point. So this means that the minimum possible value that you're going to have for a significant is going to be 1, and the maximum possible value that you can have is 2. But obviously you are never going to reach 2, right? So we have two different brackets to illustrate this. So if I write it like this, which means that with a square bracket, which says that 1 is part of this, but 2 with a rounded bracket means 2 is not part of it. But you are going to reach 2, but not exactly 2. So the minimum number that I can have is 1.000, and I continue it till 23 zeros. So that's going to be 1. And this is possible because my significant value that would be stored is all zeros. And then there is this hidden one which is not stored. So this is the minimum possible value that I can have for significant. The maximum possible value that I can have is 1.11 and all ones. So this number is not actually 2, but it differs from 2 by just 2 raised to power minus 24. As I've explained earlier, that if you add 2 raised to power minus 24 to it, in other words, 2 raised to power minus 23 to it, not 24. Okay. So if you add 2 raised to power minus 23 to it, to this number, then this will become 2. Because if you add 2 raised to power minus 23 to this number, what are you going to get? So they are all ones, right? So 1 plus 1 would be a 0. There would be a carry, and again you are going to keep on adding until the last time you are going to get 1.10. So this number becomes 2, right? So this is the smallest number that we can have. This is the biggest number we can have. But this biggest number is differing from 2 by just this amount. Okay. So we have a round bracket over here, which is going to illustrate that our significand is going to approach 2, but it can't be 2, right? Now, I come back to that point over here that we are discussing. So when operand signs are alike, a single bit normalized shift is always enough, as significant value is always going to be less than or equal to 1 and less than greater than equal to 1 and less than 4, right? So if you have operand signs equal and you want to add them, right? If you want to add them with their operand signs equal, what options do you have? So if we have two numbers like these, which are lying between 1 and 2, and their operand signs are equal, right? If their operand signs are equal, this means that you are doing either both additions or both of them are having negative signs. So you are doing an addition again. So if their operand signs are equal, then you are adding them. And if you are going to add them, so what is going to happen? Now this can happen that the second number has got a lower exponent value. So if this is S1 and this is S2, again S2 is also going to lie in the same range of significant value, right? But this might happen that this number is a small number and it needs many shifts to the right to make it equivalent, that the exponent equivalent with S1. So if you're going to shift it many times, what is going to happen is that the value reduces, and when the value reduces and you want to add them, so this means that the number is going to have the minimum value of 1. So in other words, what you are trying to say is you are adding 1 with 0. So if you're adding 1 with 0, you're going to get 1. Why are we saying 0? Because this number was a smaller number and we have reduced the magnitude and it became 0. So the final answer is going to be 1. Now let's take the other thing. When both of these numbers have the same exponent and they have their maximum values which are closer to 2. So they both have these values and you want to add them. So what are you going to get? 4. Not exactly 4, but a number which is very, very close to 4, right? So that's why we can have a final answer which can lie in this range 1 to 4. So this is a square bracket here and this is a round bracket, right? Did you get this?
Yes, sir.
Okay, so if this is your final answer, then there is one range which is acceptable, which is 1 to 2, and then there is another range which is not acceptable. So the range which is acceptable is 1 to 2. This is an acceptable range. And if your answer lie between 2 to 4, that is not acceptable. If your answer lie between a number 2 to 4, that is not acceptable. But this number which is lying between 2 to 4 will have something like this. It's going to lie between a range like this, which has 1 point, make it a little clear, which will have something like this, 0.00 and 1. So this means you don't have a single decimal point single one before the decimal point. Okay, so you need a single normalization shift in order to make it in this range, and you have to convert, you have to add, subtract 1 from the exponent. So you're going to, sorry, add 1 to the exponent, because you're going to reduce the magnitude, then you're going to increase the exponent value. So this is what is described over here, that if the result is in 2 to 4, you can reduce that by factor 2, and then you're going to right shift it and add 1 to the exponent to compensate. Okay, so this is our first point in addition. Now, when operand signs are different, this means you are subtracting them rather than adding them. So if they are different, then this means the resulting significand may be very close to 0, and left shifting by many positions may be needed for normalization. Okay, so if the operand signs are different, this means you are adding them, subtracting them, and if you are subtracting them, then this kit could be a different case. So if you have numbers between 1 and 2, uh, if you have numbers between 1 and 2 and another number also between this range, now if you want to subtract them, and they both have the same exponent as well. Now if they both have the same exponent and their significant value is very close to each other as well, then what you are going to get is a number which is going to be 0, right? Which is going to be 0, because if you are going to subtract 1 by -1, that would be 0. Okay, so you can get an answer 0 over here if their signs are different. Okay, so so 0 cannot be stored, obviously. So and the maximum that you can have is you are getting a subtraction with 2 and a 1 over here, so that would be again 1, but this number can be a reduced number as well. So if their signs are different and you want to change their exponent, if you may want to make their exponent value equal, and this number reduces, so the maximum there you can go is 2. You cannot have more than 2 if you are subtracting it. So this is the maximum that you can get. So from 0 to 2, again there are two ranges over here. 0 to 1 is not acceptable, and 1 to 2 is acceptable. So if the number lies between 1 to 2, you don't have to do anything. But if the number lies in this range, then you have to normalize it. So if you, and normalize it many times. So if you get an answer, for example, something like this number, so you have to normalize it and bring that 1 decimal point at this point, so that there is a 1 before it. Okay, so this is about addition and subtraction. So this is the final step that we have to do to make it clear, to make the addition process. So we need many shifting in case if the signs are different, and which might result in overflow and underflow. That is, you don't have space to store that number, you don't have the exponent values to store that number. Okay, so I'm going to take a break, and then I'm going to come to this this diagram over here of floating point addition. Okay, so I'm going to take a break because it's 7:30 now. So let's have a 15-minute break, and I'm going to come at 7:45. Okay, so we were late, so I'm going to come early, 7:20 or 7:40. Sorry, 7:40. I'm going to have 10 minutes break because we started late, and we don't have much time, so I'm going to have a 10 minutes break only. Okay, so I'm going to join at 7:40, and we are going to continue with this floating point addition hardware. What are the processes involved over here? Okay, I'm going to stop over here. So let's come back at 7:40.